Hello guys, welcome to Infinite Loop and another new session on data structures and algorithms. As we have seen in our previous lectures, we have discussed about time complexity and we have seen in detail about linear and quadratic, and we have seen big O of 1, that means a constant time complexity, right? So we have seen, like, we have written a piece of code and we have tried to find out the complexities for that piece of code, right? And while writing the complexities, we have did something like we have written big O of something, big O of 1 or big O of n, something like this, right? So what is this big O? Why are we generally using this big O, and why we are calling it as big O, right? So in simple terms, you can clearly see that it is something looking like a mathematical function, right? So why are we using these mathematical functions while representing the time complexity, right? We'll see in this lecture. Okay, so our main agenda of this lecture is to understand about asymptotic notations. Okay, so basically there are three kinds of asymptotic notations. One is big O, and one is omega, and one is theta notation. We can represent time complexity in any of these notations, right? So if we take a particular piece of code snippet, you can represent that code snippet in big O, or you can represent it in omega, or you can represent it in theta complexity, right? So now we will see what are these complexities in detail. Okay, so before discussing about these complexities, let me tell you this thing. I have written here something. I've written a function, like I've written different complexities. Like you can clearly see that in our previous lecture we have seen. Let me erase this, right? So in our previous lecture we have seen this complexity and this one, right? So we can see some, ascending order representation, right? So basically this is called as order of growth. Okay, so it's nothing but we simply try to represent the complexities. Like, these are only the complexities that you are going to get for any algorithm, right? So as a part of DSA, right, as a part of DSA, or as a part of solving a problem, we generally try to represent that solution in any of these complexities. Okay, so you need to remember that thing. And these are variety of complexities, like we have seen 1 n and n square, but in our future sessions also we'll look into these other complexities like log n log n, and 2 power n, like this. Okay, so before discussing about these complexities, we'll try to discuss about the notations, right? So the first notation that we are going to discuss is about big O notation. So in our previous session as well, we have represented the time complexities in the form of big O, right? So basically big O notation, what exactly is this big O notation? So basically here there are few statements that you need to see. We have written f of n, right? So basically this f of n is a function, right? Will be given with any function f of n, and you need to represent that function in big O of g of n, right? So you need to represent this f of n in terms of big O of g of n, such that there are positive constants which are c and n naught. Okay, so there are positive constants, and we are applying a simple rule here, right? Let me change the color. So we are simply applying a rule, that is f of n must be less than or equal to c into g of n. This is the rule, right? So if it satisfies this condition, then you can say that f of n can be represented as big O of g of n. It is as simple as that. Okay, so simply I'm repeating it. You have some function which is f of n, okay, and you're trying to represent that f of n in terms of another function which is big O of g of n. This g of n is another function. Okay, let's say this f of n is one function and g of n is another function, and you're representing this f of n in terms of big O notation. Okay, in terms of big O notation, and you can tell this as a conclusion if this condition satisfies. Okay, and the c is basically a constant. Okay, and remember, along with this condition or the rule, we also need to ensure that there must be some n values, specific n values, which must be greater than or equal to n naught. We'll try to see about this with an example. Okay, let me take something like this. Let me take f of n is equal to 2n plus 3. Okay, so this is my f of n. Okay, generally f of n is nothing but whatever the code snippet that you write. Like in our previous session we have seen a big code snippet, right? So instead of, we have seen like if there is one for loop we are writing n, and if there are two for loops here we are writing n square, something like this, right? So instead of writing that, we basically represent it using functions. Okay, like 2n plus 3. This 2n is nothing but 2 times n is running, and this 3 is a constant, something like that. Okay, so let's keep apart that code snippet thing, but let's try to understand about big O notation. So if we take f of n as 2n plus 3, we need to write something like this based on this condition. Okay, that means you need to write 2n plus 3 less than or equal to something, right? So what could be that something? The simple thing is there are multiple possibilities. There is nothing like one possibility, but you can write many functions, right? Let me take, I can write something like 5n. Okay, and you can check that for n value greater than or equal to 1, you can apply n values from 1 and you can check. If I take n value 1, here it becomes 5, here it becomes 5. So 5 less than or equal to 5, it's satisfying. And if I take n value as, wait, if I take n value as 2, it is 5 into 2, which is 10. And here it's 4, 2 into 2 plus 3, which is nothing but 7. So 7 is clearly less than or equal to 10, right? So you can clearly check that for values of n greater than or equal to 1, for values of n greater than or equal to 1, this condition is satisfying. Which condition? This condition. That means this condition. So this is nothing but, this phi n is nothing but, you can clearly see it can be represented as c into g of n. How? You can see here. This phi is a constant c and this n is a function, that is g of n. So g of n is our new function, right? Now we can conclude that f of n, that means you can write something like f of 2n plus 3. Okay, it can be represented as big O of g of n. G of n is nothing but n. So this is the ideology of this big O functions. Okay, so you can clearly see how we have written this 2n plus 3 in terms of n. It can be anything, right? This c into g of n, or this right side part, you can write 5n square, or you can write 6n square, or you can write n cube. You can write anything. You can write any values which are greater than this left side part, right? So what could be those values, right? You might be confused, like there are many values. Tell me what are those values. I can tell you from here. You can take any value. Okay, you can take any value from here. That means from this n and till this n power n, you can take any values, you will get the big O of n. Okay, that means these values, basically we call these values as upper bound. Upper bound in the sense, these are the kind of maximum values that you can apply for your RHS part, that means c into g of n part. Okay, so hope this big O notation is clear, right? So there can be multiple possibilities. Don't think that there is only n, but basically while representing time complexity, n is the good one, right? We can have n square also, but n is the good one. It's not like n square is wrong, but n is the good one. So this is the idea of big O notation. Okay, you can take any example of f of n and you can try on yourself. Okay, and you need to make sure that n must be that means n must satisfy this f of n less than or equal to c into g of n condition for all values greater than or equal to n naught. That means any value, right? Here we have taken 1. Let us learn about omega notation, right? So omega notation is also similar to big O notation, but there is a change of condition. You can clearly observe here, right? Instead of less than or equal to, here we have kept what? Greater than or equal to, right? Greater than or equal to. So that is the idea of this omega notation. So let us take the same example, right? Nothing difference in big O and omega, just the signs are reversed. If I take 2n plus 3, again the same example, right? So I need to write 2n plus 3 greater than or equal to something, right? So what could be that something? It is very simple. I can write n. or I can write something like 1 into n, right? Why I'm writing 1 into n? Because I need to separate this constant and g of n, right? So this 1 is my constant and this n is my g of n, right? So you can apply for all values of n greater than or equal to 1, and you can check here. If I take n value 1, it will be 5 here and it will be 1 here. If I take n value as 2, it will be 2 into 2, which is 4 plus 3 7, and here it's 2, so you can clearly see 2. And you can take any value, like you can apply 3 and you can check again, you will be getting greater than only, right? So what are we seeing here? We can clearly see that, or we can clearly write that the function f of n, that means the function f of 2n plus 3, right? And we are not writing for n, we are writing for 2n plus 3, right? So we can write this something like omega of, right? You can clearly see here I have written f of n, you can write omega of g of n. That means omega of, here my g of n is n, right? So you can clearly see how I have been identified this f of n function. So nothing different, it is similar to big O notation, just the sign has been reversed, and you need to see those values that are greater than, I mean lesser than this thing, isn't it? It must, whatever things that you write over this RHS, those things must be less than this LHS. Okay, so then you might be getting confused. Is it only that I need to take n? Can't I take another, less than n values? Like I can take root n, or I can take something like 1 as well, right? 1 is also a good one, right? If you take 1, then it will satisfy for all the conditions. I can take more less than n values. So you might be getting confused what values I need to take. It's very simple. I've written it in the beginning as well. You can clearly take the values. Okay, you can clearly take the values from here to here. So basically, as I said, these things represent omega, right? So you can use it for what? Lower bound. That means these are the least values that you can apply for your omega notation, and these are the things for big O notation, right? So clearly you have seen we have learned two important notations, big O and omega, and we are left out with one notation, that is theta notation. So let's try to discuss about it. Hope you got some clarity, right? It's very simple, only the sign has been changed and you're trying to find out the functions for that. And finally we'll come across theta notation. So theta notation is basically a combination of big O and omega notation. Okay, so you can clearly see this is what this is, f omega notation, and this is sorry, this is big O notation and this is omega notation. So you can clearly see that our theta notation, which is something like this, will try to represent it as a combination of both omega and, I mean both O and omega. So you can take the same example again, right? There is nothing new that we are going to write here, because theta notation is a combination of both big O and omega, right? So I need to write this f of n less than or equal to c1 into g of n. So my first thing will be what? 5n, right? Initially we have seen, for the first example we have seen 5n, right? For big O we have seen 5n, right? We have written 5n here. And for omega it's what? It is 1 into n, that means n. So similarly for f of n less than, greater than or equal to c2 into g of n, we'll write it as n, right? So for this, this part it is n, and for this part it is 5n. So we can write this f of 2n plus 3 or something like this as like this, right? So 5 into n and 1 into n. It is as simple as that. So this 5 is c1 and this n is g of n, or you can write something like g1 of n, and this 1 is c2 and this n is g2 of n, something like this, right? Then can you tell me how we can represent this theta notation, right? So this theta of whatever, if I take something like, wait, if I wait for some time, I can write this f of, sorry, C2 and this is G2 of n. So I can write this f of 2n plus 3 as what? Theta of g of n, right? So basically, what will be this g of n? It will be the things which are between these both, these both things, or these both, you can say something like functions, right? So it will be what? It can either be 5n or it can be n, but the most suitable part would be what? It could be something like n, right? So what we are doing in theta notation is very simple, right? We are just trying to take only n for theta notation. That means it should not be this left side part and it should not be this right side part, but it must be the values which are in between those two things. That means this is an average bound, this is an average bound, and for theta notation, remember that we are going to represent theta notation only in the form of n. Okay, we are not going to represent anything which is greater than or less than these things. So you can clearly see for upper bound, that means for big O notations we can write complexities in n log n or n square, something like this, and for omega we can write n root n log n 1, something like this. But for average, that is for theta notation, we must write only in terms of big O of n because it lies in between both of them. So that is the idea of big O notation and omega notation and theta notation, right? So these notations are very easy to understand. Okay, and for any piece of algorithm we can represent it in big O, or we can represent it in omega, or we can represent it in theta notation, but mostly we will try to represent our complexities in omega, and we'll try to see why like that, okay, in our next sessions. And this is about our asymptotic notations. Okay, so why we are calling this asymptotic notations is, hope you got it right, we are trying to make it in terms of functions. Okay, we are trying to make it as in terms of functions. F of n, we are using something like g of n, different functions, right? And we are using some constants like c. So that is the idea of this asymptotic notations. So that was about today's session, and in the next session we will try to discuss about best case complexity and worst case, what is average case, right? So we'll try to discuss these things. After discussing these things, we'll try to do some problems related to time complexities. So this was about today's session, guys. Thank you for watching, and please try to like, share and subscribe to this channel. And if you have already subscribed to channel, please try to hold on that bell icon. Thank you.